I think we can get started. So for the next speaker, we're very pleased to have Mu-Tao Wang here from Columbia, and he speaks about energy, and general relativity. So please.
Okay. Okay, thanks. It's a great pleasure to be here. I'd like to start by thanking the organizers for invitation. I was told I should give a more accessible talk to general mathematical audience. So I make an effort, so I hope I accomplish that at least in the first half. Okay? So I try to avoid any technical terms. So the title is about energy, mass, and angular momentum in general relativity. So let me just start with the story of relativity. So Einstein founded the theory of general relativity in 1915, and he actually built up the theory of special relativity, which is actually based on two axioms. Number one, the speed of light is a constant, and number two, nothing travels faster than light. And this actually addressed a major puzzle that had baffled physicists of Einstein's time. The need of a hypothetical ether in order to explain light propagation. And Einstein himself valued this kind of axiomatic approach. And he actually compared this to the formulation of Euclidean geometry in pure mathematics. So in fact, special relativity can be considered as a new Pythagorean theorem. So let me remind you what I meant by Pythagorean theorem is the following. So suppose you have 2 points on a plane, and you set up a coordinate system. And for simplicity, you always put this point O here at the origin. And you have one coordinate system, x and y, and you'll pick up coordinate x0, y0. But somehow if you pick a different coordinate system, and again, you represent this point O as the origin, and the other point will pick up coordinate in UV coordinates, unless it's U0 and V0, okay? So there are apparently two pairs of numbers. But we know by Pythagorean theorem, we actually have this equality. And general relativity is about space-time. Okay? And now you try to describe two events in space-time. But again, you can put in two different coordinate systems, or well, in physics, call it observers, to actually to describe these events. And suppose in an xt coordinate, now for simplicity, let's just assume the space is only one dimension, or observer, okay, this O event can be described as 0, 0. But this other P event is described by S equal to x0, T equal to T0. But you can see that both x0 and T0 depend on the coordinate system, okay? So Einstein likes to describe this using trains or carriages. He has a lot of stories to talk about these events. However, according to special relativity, there is an invariant here. Namely, while this x0, t0, they could be different. But once you form this expression, it's always the same. It's independent of the observer. So in this way, the Lorentzian norm is an invariant. Namely, any two observers record the same Lorentzian norm between the two events O and P. Okay? So this is the analogy to Pythagorean theorem, that special relativity actually give you an invariant. And the spacetime in general relativity is the Minkowski spacetime. Okay? And this is the Minkowski metric, and you can see distinctively they have different signature there. That account for the different sign in the Lorentz norm. And the symmetry group is just the group that keep this bilinear form invariant, and that is the Lorentz group. And this you can use to describe the relation between energy and mass in special relativity. So in particular, the energy would depend on the observer, but the relativistic mass, that is this expression here, where this pi here, their linear momentum, this quantity is independent of the observers. Okay, so observers could observe different energy, but the mass will be the same. Okay, in fact, another way to interpret this is that this energy, they are actually conserved quantities, and they are associated with the Keeling field, ddt, in Minkowski space. And pi, they are associated with the Keeling field, this translation Keeling field, ddxi. And when you talk about angular momentum in special relativity, then in this case, you always have some matter field density. This is actually a symmetric 2-0 tensor, and then you can just pair this one here with some rotation Keeling field. So this is a rotation Keeling field, and then you get the angular momentum in that direction. So this is the story of special relativity. And let's move on to general relativity. So in this case, to account for gravity, this four-dimensional space-time is actually equipped with the Lorentz metric. So this M here is a four-dimensional space, just like the familiar Minkowski space. But this G here will give you a metric that is varying at different points. But still, locally it resembles the tangent, the Minkowski space-time. So at any point you look at a tangent space and look at this Lorentz metric, you can always diagonalize it, and you can always acquire the signature, just like Minkowski space. And gravity is encoded in the curvature of the Lorentz space, Lorentz metric, G, okay? And it's actually governed by the Einstein equation. Okay, so here this Ricci is the Ricci curvature of G. Yeah, it just corresponds to certain combinations of the second derivatives of this metric tensor. And this R is the scalar curvature, that is the trace of this Ricci curvature with respect to this Lorentz metric. And the right-hand side, you have again the matter field density. Okay, so for example, if you're coupling with the electromagnetic field, then you have the stress energy tensor from electromagnetic field. Okay. But for simplicity, and this is an approach taken by a lot of mathematicians, we assume that the right-hand side is equal to 0. So there's no matter field, only the gravitational field. Okay. So once you set the right-hand side equal to 0, then just by some simple manipulation, you see that the equation, the Einstein equation, actually becomes just a Ricci equals 0. Okay, so the Ricci curvature just vanishes completely. And we'll just call this the Einstein vacuum equation now. Okay, so here vacuum just means there's no matter field. Okay. But of course, there's gravitational field, and this equation in particular has very non-trivial solutions. And this equation is just as fundamental as the Laplace equation. So this is a familiar equation, Laplace F equals 0 on R3. This is the equation that governs Newtonian gravity. But well, this equation is linear, and this Einstein vacuum equation is actually a nonlinear PDE system that consists of 10 unknowns and 10 equations. Okay, so that just corresponds to the number of entries of 4x4 symmetric matrix. So it's extremely complicated, especially when you make a comparison with this Laplace equation. However, just a few months after Einstein announced his discovery, his theory of general relativity, in the same year, Schwarzschild found the first non-trivial solution of the Einstein vacuum equation. And this is based on a lot of symmetry assumption. And you can actually, I'll just write down because this is really a very simple metric expression. So if we just choose the standard spherical coordinate system in R3, okay, so you have some R here, but you also have some angular variable, theta and phi. Then you can write down the metric on R3, the flat metric on R3, this part here. And the Minkowski metric is just by adding this term that corresponds to the tensor product of dt and dt. So this is considered to be a trivial solution. This is actually curvature just can completely vanish. And Schwarzschild's solution is actually this one here. And you can see that you simply change this dt dt component by this and dr dr component by this. So really, his assumption just reduced the whole equation, Einstein vacuum equation, into an ODE. And then when you integrate the ODE, and you actually pick up this m here. So this m here probably they just appear as the parameter that you acquire from solving an ODE. But when you look at this solution closely, you can see that this solution appears to be undefined at r equal to 0. Okay, you can see when r equal to 0 here, this term actually blows up. Okay, and also when r equal to 2m, you can see the denominator here blows up, while this coefficient actually vanishes. Okay, and we actually need to have a non-degenerate Lorentz metric at every point. So, so this r equal to 0 and r equal to 2m, they appear to be singularities of this this metric. However, the setup of the Einstein equation is completely independent of coordinate system. So you can actually choose a different coordinate system to rewrite this solution. And if you do that, you can see that this singularity at r equal to 2m, where this term equal to 0, or this whole expression blows up, is actually removable. So you can just choose a different coordinate system, and everything's going to be nice near r equal to 2m. However, r equal to 0 is actually a singularity that cannot be removed. Okay. So you can see that this, writing in this form here is somehow misguiding. If you choose a different coordinate system, you can actually remove the parent singularity, and that actually makes solving this equation even harder. Because when you write down this system of 10 unknowns and 10 equations, you realize there's actually this huge coordinate change, or the diffeomorphism group is actually acting on this equation. In one coordinate, it may appear to be singular. In a different coordinate system, you can just remove the singularity. But it turns out these 2 points, they play an even more important role. Okay? So it turns out this Schwarzschild solution is actually a black hole solution. Okay, so this is the first solution that Schwarzschild found in the same year. This is actually a black hole solution. And this particular r equal to 2m actually represent the horizon. And once the particle enters the region r less than 2m, it will never escape from the region. So this is what I mean by a black hole. So here's the picture. Yeah, so if we just represent a space-time by this two-dimensional picture, and this is a space direction, this is a time direction. And we normalize so that the speed of light is equal to 1. So light just travel along these 45-degree lines. But the axiom that nothing travels faster than light means that this, the velocity vector of any particle will be inside this so-called future light cone. And then if you just, this is actually part of the Penrose diagram here. And yeah, you can actually make it even a computer game. I mean, just imagine you have start with a particle here, and if you just follow by this rule, namely that when you travel, your velocity vector can only point to this direction. Then you can easily see that once you enter this region here, you will never be able to escape. You will be trapped inside this region here. And this shaded region is the black hole region. So that corresponds to R less than 2m. And the R equals 0 singularity is actually represented by this area here. Okay? So you start from any point in the universe, you just follow by this direction. Once you enter, you will never be able to escape. So that's the black hole region. And well, after actually a long 53 years, Kerr actually found another explicit solution. And this explicit solution is different from Schwarzschild in the sense that, well, Schwarzschild actually represents a static black hole. Okay, so it's just not moving at all. But the solution where Kerr found is actually a rotating black hole. Okay. So, well, I'm not going to write down the metric expression because it's going to be quite complicated. But again, it's just like the Schwarzschild solution. So in the Schwarzschild solution, you have a distinguished mass m over there. But in the case of Kerr, you actually have another parameter, and that is A. So this is going to be representing a rotating black hole with a mass and with an angular momentum. Okay, so that measures the rotation. Okay, so it as I said, it's quite complicated, so I'm not going to write it down. But you will be able to identify two parameters in the metric expression m and A. And I'd like to say a few words about this the development of too earlier development of black hole theory. Okay. Yeah, so far we have two solutions. One is the Schwarzschild solution that represents a static black hole. And the other one is this Kerr solution that is a rotating black hole with mass and angular momentum. And in fact, if you set the angular momentum to be equal to 0, you actually recover the Schwarzschild black hole. And too early development of black hole theory, there are so-called black hole uniqueness theorem and Penrose singularity theorem. So let me try to explain this theorem. The first one is a black hole uniqueness theorem. Okay. So this is a black hole uniqueness theorem, or what is called a no-hair theorem. That's a lot of authors, and Israel was the first one who considered, and then Carter, Hawking, and Robinson, and so forth. So what they say is the following. So just imagine you try to solve this Einstein vacuum equation, okay? And consider it as a PDE. Then you have to impose boundary conditions, okay? So in this case, we can see that both, well, I think I forgot to mention that Schwarzschild solution actually represents what is called an asymptotically flat solution, because when this R will actually, when this R parameter here, which is similar to the R parameter in spherical coordinate, when R go to infinity, you can see that this approaches 1, and this also approaches 1. So that recovered the Minkowski metric. So that's the case of, that's a flat space-time. So a Schwarzschild solution is considered to be asymptotically flat solution. So when you approach infinity, gravity becomes very, very weak, that it actually approach the Minkowski spacetime. So just imagine you try to solve this the Einstein equation, and then you impose some boundary condition. Okay, so you assume that this is asymptotically flat. Okay, and you also make some assumptions near the horizon. Okay, just like the r equal to 2m in the case of Schwarzschild. And then you also impose a condition of stationary. Okay, so it's both Schwarzschild solution and Kerr solution, they're stationary. Schwarzschild is just not just not moving at all, so it's considered a static solution. But Kerr solution is actually rotating, but really there's actually rotation symmetry along this the rotation. So once you try to solve this equation, you impose the boundary condition at infinity. You also impose a boundary condition near the horizon, and you just go ahead to solve this Einstein vacuum equation. And you actually obtain uniqueness. Okay, so in this case, if you look at a stationary solution of the Einstein vacuum equation, and subject to this boundary condition, asymptotically flatness, and also condition near the horizon, and you conclude that the solutions are actually parameterized by just the mass and the angular momentum. Okay, and then they're just Kerr solutions. Okay, so this is actually good news for anyone who work on PDE. You try to solve a PDE, the first thing you want to do is you prove the solutions are actually unique, and then you look at some homogeneous equations and you prove uniqueness first, and you try to solve this equation. So this is a black hole uniqueness theorem. And then, I'm sort of reverse the order now. So, but back in 1965, there was a Penrose singularity. Okay, so we actually tell you that these black holes, they're actually unique. There is a generic. Okay, so first thing is about black hole uniqueness, but that's actually after assuming stationarity. You assume black hole is stationary. But Penrose singularity theorem actually tell you that this black holes that you see in Schwarzschild, because in the case of Schwarzschild, really the important assumption you impose is spherical symmetry. Okay, that would reduce the whole equation to ODE. But Penrose theorem tell you that these black holes, just like the picture of Schwarzschild, they are actually generic. Okay. So let's recall in the case of Schwarzschild, okay? What we see is that, there's actually a horizon, okay? And once you enter the horizon, there's actually singularity at r equal to 0. But what Penrose come up with is to characterize this kind of surface, really just r equal to 2n surface, the boundary of this surface here, characterizing for general space-time. So what it did is, it turns out in a general space-time, you should really look at surfaces that are actually trapped. So these are actually trapped surfaces with this mean curvature or expansion less than 0. Okay, so that would be the correct generalization of this Schwarzschild r equal to 2n surface. And the statement is just under some other global sort of conditions that once your space-time has this kind of trapped surface, then in the future, the singularity will actually form. Okay, so this is a more general statement instead of just this r equal to 2m, lead to r equal to 0. But now you characterize this r equal to 2m as trapped surfaces, and r equals 0 as the singularity of the space-time. Okay, and with these two theorems, I mean, we have first a uniqueness theorem for stationary solutions, and we also have a theorem to tell you that it should be generic. But as of 1980s, I mean, all known global solutions of the Einstein vacuum equations, they all actually are explicit solution, just based on symmetry assumptions, such as this stationary. Okay, but of course, I mean, such a symmetry, they don't really appear. So we actually need more general way to solve this equation, this Einstein vacuum equations, in the hope that we can actually obtain some dynamical solutions. Okay, so they're stationary solutions. They are not actually changing. And this is the so-called initial value formulation or Hamiltonian formulation of the Einstein vacuum equation. Okay, so this is roughly the picture. This is we represent the space-time in this two-dimensional picture, and this is again a space direction. But you're going to formulate as an initial value problem in the sense that this is the initial value. Okay, so we're going to see that it's going to consist of this triple here. M0 is actually a three-manifold. Okay, that represents a slice here. Okay, we call it T equal to 0 slice. And this G naught here represent the metric. So it's actually a Riemannian metric on this three-dimensional manifold. And K0 here is the second fundamental form or the momentum. It really corresponds to the first time derivative of this G0. And then you start from this initial value here, and then you try to solve this Einstein equation as an evolution equation. So really, so we can actually break down the solution into two parts. And this is about solving this asymptotic flat space-time. So we set up a boundary condition at infinity, and or you can consider this as an isolated gravitating system. So the solution breaks down into two steps. Okay, as I mentioned. Well, first of all, you want to construct some initial data set. So that is this triple here. Okay, so it turns out if this pair here is going to be a slice, space-time that satisfies the vacuum, the Einstein vacuum equation. There are actually some equations that are called Einstein constraint equations that should be satisfied by this G and K. Okay? So first of all, you need to have these Einstein constraint equations. But in particular, this M naught here is actually a three-dimensional Riemannian manifold. And the second step, it turns out you can actually, and here in this case, you have to choose a good coordinate system again, because we know the whole equation is coordinate invariant. So then it turns out the Einstein equation can actually be formulated as a wave equation. Okay, so for this G naught here, so this is considered to be the initial metric here, and this operator here is actually a nonlinear wave operator. Okay, and so then you can consider this as a wave equation where you prescribe this G naught here. And this K naught here can be considered as the first time derivative of G naught here, and then you solve this second order. But nevertheless, this is a nonlinear wave operator, so still very complicated. But at least the well-posedness can be actually be proved by Choquet-Bruhat and York. Okay, so this gives a way to generate more general solutions. Okay, it doesn't have to be stationary, and there could be dynamics associated with the space-time. And of course, this leads to the global stability of Minkowski space-time by Christopher Heinemann back in the 1990s. So they actually construct global solutions, meaning from the initial data set all the way to infinity. And also the more recent work of global stability of the Kerr black hole, okay, by Kahneman and Zeftel. Okay, so they actually have new global space-time by this construction. Okay. But we already seen this special solution, Kerr and Schwarzschild, where we can identify this parameter, mass and angular momentum easily. But what would be the mass and angular momentum for this more general space-time? There are actually no distinctive parameters, placing in the metric expression. Okay. It turns out, so in the 1920, with this Hamiltonian or initial value formulation, so it's ADM, so Arnold with Desser-Misner, they actually come up with this definition of ADM mass. And this is actually defined for the total mass of this initial data set. Okay? And this is often referred to as special infinity. Okay? You sort of set up a coordinate system and you want to view from special infinity. And here there's actually this ADM mass. And I think fortunately this expression already appeared in many of the lectures before mine. So I just saved the trouble of writing down the expression. This is an ADM expression. But there's actually, but this is for initial data, okay? But after it evolved, okay, and in particular, because of wave nature, there's actually radiation. So there's another mass that is defined, and this is often referred to as null infinity, okay? And this is a mass after radiation, or for a distant observer. And this was defined by Bondi back in 1962. Okay. And there's actually an associated formula that is called a Bondi mass loss formula. Okay. And it sort of gives you one of the first theoretical verification of the wave nature of gravitation. Okay. So let me show you a picture here. Okay. So, well, the initial data, of course, it will correspond to this picture here, right? This is initial data, and the ADM mass is actually defined at the infinity of this time slice. But for the bounding mass, okay. So what happened is, so this is again is a space-time picture, but with this radiation, so this mass will radiate away along this null direction. 45-degree direction here. So the mass will radiate away. And then in this case, you want to measure the mass after radiation, okay? So in particular, you want to measure at the infinity of these slices, okay? So this is what is called a null infinity, okay? And now you can see that this is just depict the mass loss formula of bounding, okay? So you may have the first time slice here, and this is usually referred to as a retarded time. So this is the first retarded time here, and you measure the mass m1, and you notice that you're measuring this at infinity. Okay. While when you have a second retarded time here, this is m2 here, so this mass is equal to m2. Okay. But you can see that the mass will radiate along this 45-degree null direction. So the conclusion is that the mass at m1 is actually greater than the mass at m2. So the mass will actually radiate away along the null direction. And of course, these two are of different nature, but this one here is actually particularly interesting because this is what we actually observe. Okay, so usually you can consider this is actually a gravitating system here. So you have matter here, or you have a black hole here. But we as observer, we are actually very far away, and we are actually sitting at null infinity. So this is often, it's often referred to mass for a distant observer. Okay, and it's come up with this bounding mass loss formula. Yes.
We're sitting at, you might say, null infinity.
Yeah.
We aren't able to calculate it. We don't observe it.
No. But yeah, but best you can do is probably you can see a more solid part along a certain angle. Yeah. Yeah, we need help with with other friend in the universe. Okay. And here comes the Parsi mass theorem, which you probably heard about in this conference. So this Parsi mass theorem for ideal mass, okay, and also for bounded mass, okay. So the ideal mass was established by Shen Yao and also by Wicken here, by actually very different method. And there's also the positivity of the bounded mass by Shen Yao or by Horace Perry. And all these are actually back in the 1980s. Okay. And it shows that the total mass of an isolated gravitating system cannot be negative, even after radiation. So even after radiated away, you still cannot be negative. Okay. And the theory is actually subtle because the following. So although I didn't actually write down this expression for the ideal mass, but this ideal mass is actually written as a flux integral at infinity. Okay. So as opposed what we usually think about a mass, I mean, we in multivariable calculus, you know that to calculate the total mass, you just take the mass density and you just integrate, and you're going to get a total mass. Okay, but these masses, the ideal mass or bounded mass, they are actually not defined as a bulk integral, but they were actually defined as a flux integral at infinity. Okay, so that made the proof actually very difficult. And the reason for that is, I talk about this matter field density, where in special relativity you can use it to calculate the angular momentum. But for gravitation, okay, for gravitational field, okay, by Einstein's equivalence principle, it doesn't have density. So there's just not a tensor or a function that is defined pointwise that represent the density of gravitation. Okay, so this is really in physics this is Einstein's equivalence principle, but in mathematics it just corresponds to the fact that at any point you can actually choose a coordinate such that the first derivative of your metric vanish totally at this point. Okay, so you cannot really find a density for gravitation. Okay, so now I want to sort of switch gear to talk about something related to my work. That is to we really try to resolve this fundamental issue with gravitation, because there's no density. So whenever you try to define mass or even define energy, you cannot really integrate. There's nothing to be integrated, and the best you can do is to to represent it as some sort of flux integral along the surface. So here come up with the idea of a quasi-local mass, and if I'll talk about quasi-local angular momentum. So the idea is that the one that we just talked about, it just corresponds to some isolated gravitating system, and you just define a mass at infinity. But you can think that this will be very useful if you can actually measure the mass or angular momentum on a finite extended region without going all the way to infinity. Okay. And this is referred to as quasi-local mass and angular momentum. And you understand that, well, we cannot really just find the integral over the finitely extended region. Okay, so the correct way is try to read out this information from the boundary surface. Okay, this is also due to some expectation of conservation law. So this is actually considered to be the number 1 and number 2 major unsolved problems of general relativity by Penrose. And as I mentioned, the challenge is that there's nothing for you to integrate. So even on the finite extended region, the best you can hope is actually to look for the expression that is defined on the boundary. Okay, so this is going to be like, you imagine you have a ball here, a 3-dimensional ball, and you have a boundary surface And you try to read off the informations of these conserved quantities from the boundary surface. So a lot of people work on this quasi-local mass and angular momentum. So Hawking mass was actually extremely powerful in some scenarios, and also Penrose and Brown-York mass, and also Barnick as a mass. Okay. So I just want, but we also just work with Yao. We also come out with a notion of quasi-local mass. And later with Pauling Chen, we have a definition of quasi-local angular momentum. But I just want to describe to you some of the recent development that we found quite interesting. So this is related to what is called super translation ambiguity in general relativity. Okay, I think it was maybe started in 1960s. Okay? So very recently we were able to apply our theory of quasi-local mass and quasi-local angular momentum to find a way to resolve this super translation ambiguity. So what is this ambiguity? So this ambiguity concerns the definition of angular momentum for distant observers. So in particular, the amount of angular momentum carried away by gravitational waves. Okay, so there's actually a picture here. Let me show you this first. So this is actually from an article on Quantum magazine. Okay, so this dumbbell-shaped object actually represents a binary black hole. So these two represent two black holes, and they're actually rotating about each other. Okay. And these eyes represent distant observers. Okay, so when we look at a binary black hole rotating about each other, and we want to get a measurement of the angular momentum carried away by gravitational waves. Okay, so while the amount of radiated mass, okay, is actually well defined by the boundary mass, okay, and in fact, actually pick up this. Well, I'm referring to boundary mass, but it's actually boundary energy, yeah. But I think the energy momentum, there's also a monotonicity formula for the energy momentum. The one originally formed by boundary was actually the energy, but you can also come up with. Yeah, right. Okay, so let me just show you this. Right, this is the announcement by LIGO and Virgo collaboration. The announcement of the first detection of gravitational wave back in September of 2015. And so you can see that in this I quote here, in the source frame, the initial black hole masses are 36 and 29. And the final black hole mass is 62. So you do some simple arithmetics, you realize there's 3 units of mass that is radiated away in gravitational wave. So this is the one that is referred to the boundary mass. So if you think about mass, and if you want to compute the mass radiated away or carried away by a gravitational wave, then there is this well-defined notion of boundary mass, okay, and it is well-defined. However, there was this existing definition of angular momentum that come together with boundary mass, and that we'll just call it a classical angular momentum. Okay? And yeah, and I think it was first written down by Dre and Strobel, and it was actually rediscovered by other authors. It's in different meanings. However, this definition, but I think they all recover the same definition. That is what I call a classical angular momentum. However, this classical momentum actually leads to discrepancy in measurement by different observers. Meaning that if you pick up a different observer, when you look at the same system here, then different observer will actually pick up different angular momentum flux. Okay. Of course, we have to accommodate. I mean, in general, angular momentum is not really invariant. They're actually, there's a covariant formula when you translate your observer. But even you discount the ordinary translation, then different observers will actually will record different angular momentum flux. And this is what is referred to a super translation ambiguity. And in fact, you can actually prove that, just give me any number, then I'll be able to find an observer that observe that amount of angular momentum flux. But our theory of quasi-local angular momentum offers a solution. Okay? So it actually provides a new definition of angular momentum. Okay? And this is actually a very explicit expression. I mean, I can really write down this the whole formula, but a very explicit formula here in terms of this so-called boundary sex coordinate. And it's actually taken from the limit of our quasi-local angular momentum. And it's different from the classical term, from the classical angular momentum. So there's actually an astral correction term. But this new definition is actually super translation invariant, meaning that it's actually independent of distant observers. Okay. So for this new definition here, any observer will actually record the same amount of angular momentum flux for a system like this. Okay, so yeah, in the rest of the time, I want to get to a more technical part, and but I don't want to describe it in angular moment. The one after taking limit. In fact, this calculation was actually very difficult. We found a definition of quasi-local angular momentum back in 2000, and it's actually 2009. No, 2015, we found the definition of quasi-local angular momentum. But it took us several years in order to compute the limit. Okay? But I think I'll just mention about this, the definition of quasi-local mass and angular momentum, because I think that actually has even more applications. So let me just tell you how we actually calculate this. But before, yeah, let me just mention that there are actually other modifications of the classical angular momentum. So yeah, a different group of people offer different way to modify the classical angular momentum. But all these modifications, they actually happen at now infinity. Okay? But while yeah, let me just explain our approach. Our approach is to define this one quasi-locally just for any finite surfaces, and then you just expand your surface to infinity and take the limit. Okay, so as I mentioned, in 2015, we have this definition of quasi-local angular momentum, and it's actually based on theory of quasi-local mass, which Yao and I came up with back in 2009. So, what is the? I actually give you the full expression here. So this is actually a Hamiltonian approach of defining energy at a quasi-local level. So what we're do is the following. So imagine what we want to do is we have a finite region in space-time, okay, just like a domain here. So the boundary is actually two-dimensional surface, and we try to define more expressions on the boundary surface in order to read off the mass and angular momentum of the enclosed region. Okay, so what we're going to do is we're going to take a physical data on this two-dimensional surface. So this is just surface sitting in your space-time. It's a two-dimensional surface, topological S2. And the important data we're going to pick up are the induced metric. So the sigma here represents the induced metric on sigma, because you assume the surface is space-like. So this is actually a Riemannian metric. You can just take as sigma to be a two-dimensional sphere. So this is just going to be a Riemannian metric on a two-dimensional sphere. And then the other data we're going to take is this is what we call a mean curvature vector. So this is the one you use to describe the expansion. It just measures how the surface area will change when you move the surface. But it's actually a section of the normal bundle, or a normal vector field of sigma. And then what we're going to do is we're going to take this physical data here, this two-dimensional metric, and also this normal vector field along the surface. Then we actually have an equation, what we call the optimal isometric embedding equation. And what we're going to do is we're going to embed this one here into Minkowski spacetime. So that is a flat spacetime. And we're going to use this one here as our reference. And this image is going to be a reference surface in Minkowski space. Okay. And it's going to have the same induced metric. That's why this is called isometric embedding. Okay. So we use this isometric embedding to anchor the induced metric. So once you anchor the induced metric, you anchor the intrinsic geometry. And then we're going to compare the extrinsic geometries of these two surfaces. Okay? So this hope is that the gravitational field will be reflected in this extrinsic geometry. So this is a picture here. This is isometric embedding. So this is a surface in space-time. So it's two-dimensional surface. We pick up the induced metric and also the mean curvature vector. And then we do an isometric embedding, and so the induced metric on this reference surface is going to be the same as this one here. But however, the mean curvature vector, which sort of dominate the extrinsic geometry, will be different, okay, and it's actually sitting in a different normal bundle. But we're going to extract, data from this sigma h and also h0 here. So to be precise, I mentioned that the mean curvature vector is a vector field, okay, normal vector field. But first of all, we can take the measurement, so that will actually give us a number. And in fact, we're assuming that this mean curvature vector is a space-like vector. So this is a normal, and this is going to be a positive function. And also, it's a section of the normal bundle. So we actually provide you a frame to define a connection. And this alpha h is a connection one form of the normal bundle, defined by this h here. And the important thing to note is that, these data, they're totally independent of coordinate system. You take any coordinate system in your space-time, once you have a surface here, then these are geometric quantities that are independent of the coordinate system. And then, but notice that this isometric embedding is actually a underdetermined system, because when you solve this isometric embedding, you solve a metric, Riemannian metric on two-dimensional surface, three components, but you're actually doing embedding into a four-dimensional space. So this is actually a system of three equations with four functions. Okay. However, what we're going to do is we can first fix some time function, and we solve the following equation. So this basically just tells you that you take this tau here, this time function, and this is going to be the metric on basically the projection of the surface on a certain R3. So this is basically the isometric embedding equation. The sigma here is given, and you have you have four functions, that's x0, x1, x2, x3, that represent the four coordinate functions into the Minkowski space. And this is basically the isometric embedding equation for the embedding given by x0, x1, x2, x3. Okay. So this actually gives you a configuration of sigma, okay? And then we extract the reference data accordingly, okay? So this is going to be a surface there, so there's going to be a mean curvature vector field, and you can extract this one form associated with it. And then for these two sets of data, we introduce these two functions, okay? This is rho and this is j here, okay? And you recall this tau here really corresponds to this x0 here. And this is the time function, and it's a function on the surface. So you can take the Laplacian with respect to the induced metric, and this is the norm of the gradient. So you can see that rho will actually depend on the mean curvature of the reference surface and also the mean curvature of the physical surface. And there's also this j here, which is essentially a one form. Okay, we have rho coming from here, we have tau here, and there's this expression, and there's this two, the difference of these two connection, one form of the normal bundle. But again, this rho and j, they're just totally independent of coordinate system. And then you can actually integrate this rho here, okay? And that will actually give you the quasi-local energy of this embedding, okay? But recall, I mentioned that this isometric embedding is actually an underdetermined system. So you do have one functional degree of freedom that corresponds to basically this time function here. So what we do is we look at this energy here, okay, and then we consider the Euler-Lagrange equation for this energy here, okay, and well, after a lot of calculation, and in fact, this is why we come up with this expression here. You realize that the Euler-Lagrange equation of this isometric embedding equation is actually just a divergence of this one form equals 0. Okay. But now you actually have four equations for four unknowns. So this is something you can actually expect to have some well-defined solution. Then, and in particular, you can prove that for surfaces near the null infinity, this system, okay, that's this equation 1, that will correspond to the isometric embedding equation. Okay, there are actually three equations here, because they correspond to the AB index here on the surface. And there's a fourth equation that is this one here. Right, sure. Right. Then you can prove that near null infinity, this whole system they can actually be solved and uniquely. And then how do you get the angular momentum? Since now you have a distinctive surface in the Minkowski space, so you can take advantage of the rotation killing field in Minkowski space, and you can just transplant this rotation killing field of Minkowski space back to your physical surface, and you pair with this J here, the one form that I just mentioned, and that is our definition of quasi-local angular momentum. And the limit of this quasi-local angular momentum defines the new total angular momentum at null infinity. Okay. And the interesting thing is that at first we took it as a check of our definition. We want to make sure it's actually consistent with the classical definition. But somehow the answer is actually different. There is actually a term here that is void from the classical definition. And that term is coming from the solution of this isometric embedding equation. Okay. But after we put this term back here, we realize we can actually prove that the new definition is actually supertranslation invariant. So in retrospect, it's actually not surprising because the way we started with, all the definitions are actually independent of coordinate system. So at the end, it's still a coordinate independent quantity at null infinity that is free of this supertranslation ambiguity. Okay, so I should wrap up. So at the end, I just want to show you some pictures. I think that's a nice way to. So this is again this is a I guess dramatized picture of of the first detection of gravitational wave in 2015. And you can see there's two black holes. Actually, one should be slightly larger than the other one. So they're rotating about each other, and at the end, they merge into a single black hole. So, so that's the whole, it's this whole gravitational wave. And yeah, this is the paper of the mass. And we're hoping that we'll be able to make some similar calculation here with regard to the angular momentum. Okay, I think I'll stop there.
So
Is there any hope that these definitions are useful for problems like cosmic censorship or other unsolved problems involving general relativity?
Well, the truth is, here we're actually taking advantage of the asymptotic flatness. Because solving these optimal isometric embedding equation, they are actually extremely difficult. So although we have some existence theorem, we have some uniqueness theorem, but in practical, we still have to do spherical harmonic functions and solve it term by term. So I don't know. In the future, maybe we have better ways to implement these calculations.
to look for application from field behavior, any closer local mass.
Yeah, but
So,
yeah, even for this kind of binary black hole, could be a long shot. But I'm thinking, I mean, one more likely scenario will probably be this kind of EMRI things, when you take advantage of the different ratio of mass and then play around those parameters.
Does the quasi-local mass of spacetime generate new gravitational field?
New gravitational theory. Well, I think we're still within the framework of classical general relativity.
My question is, the mass of spacetime generate new gravitational field?
I don't think we were able to generate new gravitation theory. We're still working within the framework of Einstein theory. Yeah. Gravitational field. Yeah, maybe just a different way to look at gravitational field. I mean, now we can actually, focus on a finitely extended region instead of going all the way to infinity.
I see that there are observational data from gravitational wave observation, being that how much the kick velocity is after the black hole merger. And also, on the other hand, numerical relativity can certainly give us simulation data for, let's say, the angular momentum of the remaining black hole. Right? So is it possible to use a formula to calculate the, I guess if we know the remaining angular momentum, it will be, let's say the angular momentum emitted by carried by the gravitational wave. So we should be able to predict this kind of kick velocity.
Yeah, I think there was some argument that saying that for some compact binary system, the difference between classical one and ours, they're probably not noticeable. But you can expect in other scenarios. I mean, and I think it's from one of the Max Planck researcher claimed that maybe in 2030 we will be able to notice the difference between the classical one and ours. But I mean, I don't do observation and I don't do numerical simulation, so I don't know. But yeah, but that would be really interesting to see. I mean, the difference that this term makes.
So let's thank Mu-Tao again.
But but for cosmic censorship, you have something more concrete that